How do you know a digital credential is genuine, unchanged, and safe to share? In this module, we'll connect hashes, keys, signatures, and zero-knowledge proofs to the issuer, holder, and verifier flows that make verifiable credentials trustworthy. We've already built the identity foundation, models, DIDs, and how verifiable credentials relate to JWTs. Now we'll go deeper into trust itself, with hashes, key pairs, signatures, encryption, and key management. Cryptography works like a tamper-evident seal on a digital credential. The issuer signs the credential with a private key, and anyone with the right public key can check two things. The contents have not changed, and the signature came from that issuer's key. That check can happen later, even offline. But verification is not the same as trust. The verifier still needs a policy for deciding whether that issuer is acceptable. A hash function is like a digital fingerprint machine. It can take a tiny value or a large credential document and produce a fixed-length digest. The same input always gives the same digest, which makes hashes reliable identifiers. But change even one character, and the digest should look completely different. A good cryptographic hash is also one way, so the digest cannot reveal the original data. In verifiable credentials, hashes help detect tampering and bind data into proofs and signatures. These three hash properties protect against different attacker goals. Pre-image resistance means a digest cannot be reversed into the credential data behind it. Second, pre-image resistance means that once a real credential exists, an attacker cannot create a different credential with the same digest. Collision resistance is broader. They cannot find any two different inputs that hash alike. If these properties fail, identifiers, commitments, signatures, and proofs can be quietly substituted or forged. In credential systems, hashes usually work behind the scenes. A credential may be normalized, hashed, and then signed, so everyone signs the same representation. Hashes can also shorten identifiers, power Merkle proofs for revocation or membership, and create commitments used in zero-knowledge proofs. So the hash is not just storage plumbing. It becomes part of trust. The private key is the authority stamp. It creates the digital signature on a credential, so it must stay protected. The public key is different. It can be shared through a DID, certificate, or registry, because its job is only to verify that signature. If the signature checks out, the verifier knows the credential came from the key controller and was not changed. Never expose private keys. Losing one can break issuance, revocation, and proof of control. Digital signatures usually start by turning the credential into a consistent form, hashing it, and signing that hash with the issuer's private key. The resulting proof travels with the credential. Later, the verifier uses the issuer's public key to check that the proof matches the credential data. Any change to the data breaks the check. Still, a valid signature proves integrity and key control. Policy decides whether to trust it. A verifier does much more than confirm a signature. It validates the cryptographic proof, including the signature, proof type, timestamp, verification method, and intended purpose. It resolves the issuer's keys through a DID document or trusted key system. It checks credential facts like expiration, revocation status, schema, issuer, and subject. Then it applies policy. Is this issuer trusted to make this claim for this specific use case? When credentials are structured documents, the signature cannot depend on accidental formatting. Two JSON objects can mean the same thing, but produce different bytes because fields are ordered differently or whitespace changes. Canonicalization solves this by turning the data into one stable form before hashing and signing. Data integrity and linked data proofs use this pattern. JWT credentials take a different route. They sign a compact encoded payload, reducing, but not eliminating, serialization concerns. Signature schemes are engineering choices, not just cryptography choices. ED 25519 is fast, modern, and common in DID and VC tooling. ECDSA is widely compatible, especially with browsers, blockchains, and older infrastructure using P256 or CCP256K1. BLS is more specialized, but useful when aggregation or advanced privacy proofs matter. The scheme you choose affects key formats, proof types, verifier libraries, and future zero-knowledge options. There is no universal best signature scheme for credentials. ED 25519 is often a strong default for new controlled systems because it is fast, simple, and harder to misuse. ECDSA makes sense when integration with existing wallets, certificates, browsers, or blockchain tooling is the priority. BLS is different. It can combine many signatures into one compact proof, which can support multi-issuer or privacy-oriented designs. Choose based on standard support, threat model, and library maturity. A DID is the stable identifier, but the DID document is where trust material is discovered. When a verifier checks a credential, it resolves the issuer's DID, reads the document, and finds the verification method authorized for the right purpose. For VC issuance, that is usually assertion method. The method points to a public key, which is used to verify the signature. If keys rotate, the document changes, while the issuer's DID can stay the same. Treat keys as living security assets, not one-time setup. Issuer private keys belong in HSMs, KMS platforms, or hardened secret stores with strict access control and audit trails. Rotation should happen on a schedule and immediately after suspected compromise without breaking verification of older credentials. Did documents publish new verification methods and disable unsafe ones? And remember, key revocation is different from credential revocation. One protects signing authority, the other invalidates claims. Public key cryptography gives verifiable credentials their trust foundation. Hashes create reliable fingerprints. Keys and signatures let issuers prove authenticity and let verifiers check it independently. Strong key management keeps that trust intact. Next, we extend these building blocks into zero-knowledge proofs and selective disclosure, where verification becomes more privacy-preserving.